This is Jeff Lendermon with GoEngineer. I'm an applications engineer concentrating on the plastics simulation software. So I'm the plastics specialist within GoEngineer. I've been with the company a little over 2 years. I've got 30 plus years experience in the injection molding business. It's been quite a joy working for GoEngineer, getting to use all my expertise and still getting to communicate and relate to all the engineers that I get to deal with. Planning on showing the basics in SOLIDWORKS Plastics Standard with the basic setup of what you need to do to be able to get into and run Plastics Standard. It's such a great tool to use, and I'll explain some of the things that we can do in validating plastic part designs using the SOLIDWORKS Plastics Standard simulation tool. So I'll give a brief overview of the three packages. SOLIDWORKS Plastics, it was developed to help users predict and avoid manufacturing defects during the earliest stages of part and mold design. So you're eliminating your costly mold rework, improving your part quality, and decreasing the time to market. So SOLIDWORKS Plastics Standard is for part designers. It's going to answer the questions basically, will my part fill? It'll show us where our weld lines and air traps are, and it'll also indicate areas on your part design where you may have sink marks. This is a bad cosmetic defect in the injection molded parts. And we also have the ability to work with multiple gates. So instead of running just a single gate on a part, we can look at multiple gates in different gate locations. So as I said before, we're going to concentrate on Plastics Standard today, but Plastics Professional would be the next step up. Plastics Professional is more geared toward mold designers. So all the tools that are in Plastics Professional are geared more to someone that's going to design and build the injection mold. So we're looking at multiple cavity analysis and runner balancing. That's a very powerful tool that I really like in the professional tool. If you're doing insert and overmolding, then your inserts and overmolding are part of the professional package. We've got valve gating, so hot runner systems, valve gating, that type of thing. It's all in professional. If you're running fiber-filled materials, you can do a fiber analysis, which will basically track the fiber orientation through the flow of the material. Also, we've got co-injection and gas assist, a part mass versus time plot, which is basically like a gate freeze-off study, and then reaction injection molding. So if you work with thermoset materials, you'll have to have Plastic Professional to access the thermoset material library. Not a very big library right now, but I hear SOLIDWORKS is working on increasing the material database all across the plastics platform. And then finally, Plastics Premium. This is the highest level package. So you get everything in Standard and Pro and Premium. They've included the advanced cooling analysis and warpage analysis. So these two go hand in hand. The cooling analysis will go through and analyze the variable cooling in your mold. An injection mold is never a completely uniform wall temperature. So being able to run the cooling analysis hand in hand with the warpage analysis is really great. So I've got a few slides. In this webinar, I'm going to cover the tools within SOLIDWORKS Plastics Standard that will help designers validate their plastic part design. The key topics that I'm going to cover are part design, which when we're looking at designing a part for injection molding, we want to concentrate on the uniform wall. I'm going to concentrate on the part mass and cycle time on this part to see if we can possibly reduce the part mass and in turn also reduce the cycle time, which in the end is going to reduce the cost of our part to produce it. Beyond that, I'm going to go in and cover the setup, which includes meshing and the material and the injection location. When I jump into the software, I'll show you those three things, and that's basically the only three things you really need to set up to do your first initial analysis on an injection molded part. And then finally, we'll concentrate on the results of sink marks, and we'll look at our fill time and cooling time in this part that I'm going to pull out of this robot arm. We'll analyze this one single part, and I'll be able to show you the cost savings that we can do on a single part. So imagine this robot that has all of these different parts in it. We could go through and validate the designs of each individual part and possibly even reduce the cost of the whole arm. So when we're looking at the injection molded plastic part design, uniform wall thickness is really important. It's going to promote our balanced filling, which will allow for uniform cooling, which also allows uniform shrinkage and less warping in the part, because warping is caused by non-uniform cooling in a part. We'll also look at the part mass on our part. So like I said before, I want to reduce the mass with thinner walls, and a thinner wall will also reduce our fill time and our cooling time. We'll be able to run an analysis on different configurations. And then finally, I'll look at my cycle times, which include the filling time and the cooling time. So your cycle time has a direct impact on your part cost. So remember, if we're designing a plastic part and we're trying to validate this plastic part for the injection molding manufacturing process, the SOLIDWORKS Plastics tool is a really handy tool for a part designer. You can do all of this before you even send this part design to a mold building house or something like that. So if we're just concentrating on the design and engineering aspect of it, and we're not the injection molder or we're not the mold producing house, it's still a really good tool for you to use, so you don't have to kick this part design back and forth across to your mold builder and all of that. You can go through, analyze your part, find your non-uniform wall thicknesses in the part, see how the material flows through on different gate locations, identify your weld lines and sink marks, make some of the changes to your models, and then you'll be able to then kick it over the fence to your mold builder, and they'll have a whole lot better, more robust part to start with before they have to send it back to you. So I'm going to cover basically the meshing, injection location, and a couple of other things in the PowerPoint first before I jump into the software, and then I'll walk through the setup on this part model in the software, and then we'll be able to show you the results and changes that I made. So in order to run a flow analysis in SOLIDWORKS Plastics, the first step we have to do is mesh the model. So there's two different mesh types available in SOLIDWORKS Plastics. There's a shell mesh and a solid mesh. So typically a shell mesh is used on thin wall parts for obtaining quick results in the early stages of a process. Really, you want a really uniform wall thickness for a shell thing. So if it's just a basic shell case with no ribs or not a lot of radiuses, no bosses, things like that, and your wall thickness is one complete uniform thickness, then the shell mesh works pretty good just for seeing the basic flow of the material through the part. Typically, I always use the solid mesh. So solid mesh provides more accurate results for any model. If it's thick or thin, it meshes internally in your model, so you get the flow of plastic through the model, around all your cores, and everything like that. So your solid mesh is going to have greater accuracy results for models with complex and intricate geometry. So when we look at a solid mesh, we have options for tetrahedral versus hybrid mesh. The hybrid mesh is something really nice that SOLIDWORKS Plastics has in it, because to get a good, accurate result out of the plastic simulation, SOLIDWORKS recommends that we have 5 mesh elements across the thickness of our part. If we're meshing with a tetrahedral mesh, as in the picture at the top, we would have to make more refinements to the mesh elements to get enough nodes going across the top. So if you look at the little triangles, those are your mesh elements. To get 5 mesh elements across this thickness, our top picture looks like it has maybe 2 or 3 across the thickness. So it's going to require more elements, which requires finer mesh, and then you get more elements in your model, and it takes a whole lot longer to process. So when we look at a hybrid mesh, this lower picture in the slide, you can look, it's got 2 layers of like extruded triangle mesh elements on the outer skin of the part, and then it infills the rest of that with tetrahedral mesh. So if your wall thicknesses are different in different areas, you'll always have at least 5 layers of mesh. It works really well. You get a lower overall element count, so your processing works a whole lot faster. The next step after we mesh our part is our material selection. So the SOLIDWORKS Plastics database has over 4,000 materials available to choose from. It also has a user-defined database. So if the material's not in the software, you can go to the material manufacturer and request the viscosity data and the data that SOLIDWORKS Plastics needs to run properly, you can get that data from the material manufacturer, and you have the ability to enter your own custom material in this. So with that being said, new in 2019 Service Pack 3, the SOLIDWORKS development team just implemented a download area in the 3D Content Central. So 3D Content Central is something that's been in SOLIDWORKS for a very long time, where you can go in and download supplier content for parts and things like that. Well, now they've added an area within 3D Content Central to bring in injection molding materials out of there. So instead of having to wait for the next service pack for new materials to come out, the SOLIDWORKS development team are going to be loading new materials into 3D Content Central. So we'll have immediate access to it when they put them in there. And then when the new service pack comes out, they'll be in the new service pack. And then finally, we need to specify our injection location. So as I said before, Plastics Standard, we have the ability to specify a single or multiple injection locations. Now we have the option in 2019, we have geometry-based injection location and we have mesh-based. Previously, everything was mesh-based. What a geometry-based injection location will do, it'll allow us to select a face, maybe using a split line or something like that, or we can just put a sketch point on our model where we would like to try our injection location. So when we specify that during the geometry-based, it's going to stay tied to the model. If we use a mesh-based injection location, every time we remesh the model, we'll have to go back in and reassign the injection location again. So the geometry base isn't just another one to speed up the workflow in SOLIDWORKS Plastics, and it seems to be working really well for me, and I'm glad to see those changes. So in the future, I believe that more and more of the settings inside of plastics will be geometry based. And then finally, we're going to look at the results on this model. We'll look at the fill time plot. The fill time plot represents the time it takes for the cavity to fill during the injection phase of the molding process. SOLIDWORKS Plastics Standard only has the filling phase. The packing phase is part of SOLIDWORKS Pro. So all you'll be able to do is see how long it takes to fill it with plastic. You won't have any of the packing results after that. And then we'll also look at sink marks. So a sink mark is going to display the area of the part that may have sink marks on the part, and they'll show up in, generally they show up in thicker regions of the part. A lot of errors that happen during the plastic part design phase is there may be some bosses that are too thick, or maybe if you have ribs in your model and you have ribs with draft and they're drafted out to the surface of the model, they may be too wide at the surface of the model and create a thicker profile. So those things will show up in the analysis. In our cooling time result in SOLIDWORKS Plastic, the predicted cooling time is determined when 90% of our part temperature is less than the material ejection temperature. So 90% of the model may be less than the ejection temperature. If that 10% of your model is still above the ejection temperature, and it's a really thick section, that could cause vacuum voids where the material is trying to shrink away from the walls when everything outside is already solidified. Your internal molecules in the plastics, basically, they just rip themselves apart and create a vacuum void inside. Or you end up with reheating of the plastic, and then it starts creating a sink mark on the outside of the part. And then finally, air traps on the model. So your air traps are areas on the model that indicate where air may become trapped. Usually the last places to fill in a part. So I'll show you on this model how that's identified as well. So I've got this model. SOLIDWORKS Plastics is an add-in in SOLIDWORKS, so it works within the SOLIDWORKS interface. You can work directly on a model in SOLIDWORKS, so you don't have to export or import anything into it. It's just another add-in tab inside of SOLIDWORKS. So the first thing you would have to do to come over to your SOLIDWORKS add-in, turn on SOLIDWORKS Plastic. With that on, we have the command manager at the top, and we also have a tab for a plastics manager on the left. There's a getting started wizard in SOLIDWORKS Plastics. You can use that. It's similar if you've used the Simulation Express inside of SOLIDWORKS. It kind of walks you through step by step what you need to do. Or what I like to do is use the properties manager for plastics on the left-hand side. So when you first open a part, it starts, we only have boundary conditions and mesh. So it's pretty intuitive as to what you need to do next. So we know we can set any of our boundary conditions. So remember that one of the first things I wanted to do, I'll set a boundary condition for my injection location. So if I right-click on boundary conditions, select injection location, set this on point, I can select the sketch point that I have on my model that is for my boundary condition. So now we have our injection location. And then the next step, we'll go to mesh. So we have all these solid mesh options. So we have solid mesh manual, solid mesh automatic, and shell mesh manual and shell mesh automatic. So solid mesh automatic will go through and do all of the steps to create a solid mesh, but you don't get to see any errors in there. So if there's an error with your mesh, it may not mesh at all. Typically, I'll go straight to the solid mesh manual. So if I right-click on solid mesh manual, we can go through the solid mesh procedure. So Plastics Standard, you may not have these advanced options show up. That's for SOLIDWORKS Pro and Premium. So we'll have the solid mesh procedure here. Since we only have a single body in our model, we have a single cavity that shows up. If we were running SOLIDWORKS Pro and we had a multi-body, maybe we had an insert we were going to overmold that would show up as another body, we could come in and specify that that's an insert. Or we could go even further in SOLIDWORKS Premium. We can have 3D model cooling channels. SOLIDWORKS Pro, we can have 3D model runner systems too. So then we'll go next. And these are our settings to set our triangle size for our elements and nodes. The general triangle size here is basically your average part wall thickness. It's a really good point to start with. If I want to do any mesh refinements, if I click mesh right now, and we look at some of the holes, the hole isn't really represented as a hole, it's more of an octagon. So it'll do that with radiuses, they look more like chamfers, things like that. So typically instead of running with no refinement, I'll tell it that I'm doing automatic refinement. So this will go through and utilize the mesh tolerance, which is the ratio minimum triangle size from the triangle size. So it's actually trying to balance the triangle sizes from one triangle to the next. So now if I click mesh with it on automatic, we can see that my circles are more refined and everything. So we get a whole lot better mesh. It's getting better and better. Each release of SOLIDWORKS Plastics since 2016 has made improvements on the meshing procedures and the meshing workflow to speed it up. Makes it a whole lot easier to get a good mesh. So after that, the next step, if we hit next, then we get a summary of our mesh. This is where I was talking about we wouldn't be able to see any errors or any inconsistencies with our mesh in our model. First thing we want to look for, we want to make sure it's waterproof, which means there's no mesh holes, there's no holes in the mesh. It would hold liquid, you know. Number of mesh groups, it was a single body, there should only be one mesh group. Element intersections and non-manifold elements, these would be elements, if we look at like on a corner of the model, we can see how each node, each triangle meets another triangle. So a non-manifold one would be, so a point may meet over in the middle of a line instead. So it may have some geometry errors there, a really thin sliver or something like that, and it doesn't know what to do with the mesh in that area. So those type of errors would show up, and that's also another way to check your modeling. I've seen several of them where when I did the automatic mesh, it had a really refined spot in one area. It was this really thin spot in the part, and it showed up during the meshing process that you couldn't even see it in the model until I did that. And then we have what are called bad elements and very bad elements in the maximum aspect ratio. I'm going to go out of this and go to quality and explain those. So the aspect ratio is basically your length to width ratio of the triangle. So the goal is to have as close to equilateral triangles in your mesh as you can. So we're looking for an aspect ratio of less than 8. My model has 100% of them less than 8. That's really good. Aspect ratios between 8 and 20 are acceptable. So if there was any of those in there, we could ignore those. If you had a really high percentage, I might go back and refine my mesh and get that a little closer. And then your aspect ratios over 20, these we would want to fix. So if there's, once again, if there's a lot of those, then you may want to go back and refine the mesh. Or in 2018, they added this fix button that'll actually go through and try to fix the mesh in those areas, and just by changing the sizes and stuff in those particular areas. It works really well too. So then we go through the next couple of next steps, and then now we have our options for, now we're on step 6, we're looking at our solid mesh. So the first steps of it, we are creating the outer surface mesh on the outside. Now we're telling it what we want it to do on the inside between those layers. So remember, we're going to use a hybrid mesh so we can be guaranteed we have 5 layers through our thickness. And I'll simply click Create Mesh, and then we can look at the mesh inside the part. So it'll do this section view for us at this point. So we see we have the 2 outer layers on both sides, and we have 2 more elements. So we have the at least 5 elements there. So step 7 basically gives us options. We can go in and do section clipping and look at it in some other places if we want. And then we can simply hit the green check mark at the end. So once we've got our mesh, remember the next step, we can add our polymer. So I can right-click on the polymer, open the database, and then we can come in and select our polymer. So if I want an ABS, we have the ability to search. I can search for a specific material. I can come in and look at different materials. I can look up certain ones that I want. I want that one. Okay. So when we select a material, we've got all these data points. I want to point out the polymer material parameters. So if you're a part designer, you not really know everything about the injection molding process. You don't know what the melt temperature settings or machine settings or any of that are. You don't have to be concerned with it because it pulls that data from the recommended values off of that material. So it'll set our melt temperature, our mold temperature. It calculates the ejection temperature and glass transition temperature, so it knows when, at what point the part's ready to be ejected from the mold. So one of the things to remember is these. So after we've assigned our materials, the next step, there's processing parameters. I'll open the fill settings. This is the only setting that you'll have in Plastics Standard. The filling time is calculated based off of the volume of your part and the material you chose. That's something that can be changed. So if you're going in and analyzing a process that already exists, you can go in and override that value. And remember, the melt temperature and mold temperature, those come directly from the material we chose. Our injection pressure limit is set to 100 as a default. That can be changed. A lot of injection molding machines go over 200 and above now, so you may possibly want to come in here and change that based on what machine it's going into. If you don't know, then you just leave it at 100. It'll give you some indication. If your part's too thin and it goes over 100 MPa, that's kind of a red flag that you may need to change your part thickness or change something within the model, maybe your gate size or something like that. The clamp force limit also defaults to 100. That can be overridden or changed if you know what size machine it's going into. So we have pack settings and warp settings, we won't cover those since we don't have those in Plastics Standard. And then we have the boundary conditions. Since we already set our boundary condition for injection location, we don't need to do it again here. But if we were to want to go through the injection location and set it up here, we could come in, and it actually works off of the nodes. So you would select a node and it would put it there. So there's some best practices. I have another best practice video where I discuss creating the split line where you want your gate location to be and then refining the mesh in that area. What I really like about this injection location based off of a point, you can see it refined to the mesh around the point, so you get a whole lot more accurate fill pressure readings and things like that in that area because you have a finer mesh there. And then the final step is just to run the flow analysis on the model. So I'll switch to, I've got another configuration set up, so I'll switch to Plastic Study 1. So now we'll go to the results. I'll quickly go through the results that I talked about. If I right-click on my flow results, we can get those to load. And remember, I want to concentrate on my fill time, my cooling time, and sink marks on this part. We've got a lot of other results in there. Some of them are really handy. We can look at our weld lines and air traps. I'll turn those on and go back to my fill time. So the weld lines show up as these little black lines on the model. Typically, anytime material flows around a core, you're going to get a weld line, or if you have multiple injection points, you have two flow fronts, so you'll have weld lines there. So in this case, the way the model is set up, we have a fill time of 0.733 seconds. I want to go to my cooling time and look at it. My cooling time is showing that I have a cooling time of 10.233 seconds. And maybe I can look at my temperature at end of cooling, and we have some areas in our model that are still at the end of cooling. They're still 231 degrees, which is pretty high, 231 degrees C at the point the part's being ejected. So what would that possibly cause is sink marks. So if we look in this area on the model, we've got sink marks here and here. We can go to another view, and we can look at this other view. So this is the other side of the part. So we've got sink marks in this area. Look, this is a really blocky part. So maybe we need to go in and change the geometry in this part on our model. I've got some other areas too that are not quite sink marks, but you can see there's a color differential here, and in these walls here. So if we look at our model, we see the sidewalls on this are a lot thinner than the sidewalls on this. So maybe we can go in and redesign this model some, reduce some of the wall thickness, and then we can go and rerun another analysis. So one of the great things about SOLIDWORKS Plastics being inside of SOLIDWORKS, we have this duplicate study tab. That allows us to go in and specify a new configuration name, and we can start a new configuration of the model. What this does is it copies everything that we've already set up in our model. So if I switch over to Plastic Study 2, since I already did a plastic study on it, it allows me to load that study again. So if we look at the model now, we can see how I redesigned this area where it was thick-walled. I'd added some core outs in this area here, added some core out there, and went in and modified the wall thickness to make these walls equal to these. So gone through and made some changes there. And now we can go back in, and whenever you make your changes, if you make any geometry changes, you have to go back in and remesh your model. But it remembers your mesh. So, and we don't lose anything from the previous study because it's a different configuration of the part. It's really great. You can go in. That way you don't lose anything. So set up your initial study, make a run. If you make any changes, do your duplicate study. It'll create another configuration of the part, and you can make any geometry changes. You can make any material changes or gate location changes, anything like that. So you can set up multiple different iterations of what ifs, and then you could actually use the batch manager, which would allow you to select which studies you want to run the filling analysis on and tell it to run those. If I click on that, I could go in and select the file folder that has the study in it, tell it which study I want to run. I could even tell it what time of day I want it to start. So maybe I set up all my iterations at 5 o'clock in the afternoon. I want it to start then. I can start it. It'll start running the batch manager. I can completely shut SOLIDWORKS down. It'll continue to run the batch manager. It's really nice. In the morning, you open up SOLIDWORKS, go back to your part file. You can look at all the results from all of them. So now let's go back and look. We'll look at our flow results from our newly updated model. We can look at our fill time now. It's down to 0.487 seconds from, it was 0.7, remember that. We can look at our cooling time. Cooling time is down to 4.4, so we knocked almost 6 seconds off of our cooling time in our model. And then I can go back and look at my sink marks. So I still have some areas, but it's not as high of a sink mark area. I mean, your scale is still going to be from blue to red. So red's not necessarily bad. It's just that's the highest value in there. So we have a whole lot better look on the side, a whole lot less chance of having an obvious visible sink mark in our part. So there's other things. If I go back to the fill time, we can watch the flow of the material into the part. That's another thing of the fill time. So we can see as it wraps around these cores, these would be areas where our weld lines would show up, right? So if I turn on weld lines and go back, run my animation again, we can watch as it wraps around the cores. That's where the weld lines show up. And turn on the air traps on the model. So one of the things we look for as air traps is to make sure your air traps are generally going to be in an area where it's like the last place to fill. So we want to make sure it's in a point of an extent in your model. So somewhere along the parting line or somewhere at the end of a boss or at the end of a rib, something like that. That's an area in the mold that can be vented. So just by going through those basic steps, remember we did our injection location, we did our mesh, selected the material, ran the flow analysis. I was able to look at those results and make the changes in my model, and I was getting my model ready for injection molding. So if I can compare my study 1 versus my study 2, I did basically a cost study on them based on the national average of ABS plastic in the U.S. in 2013. It may be different now, and also based on the machine time cost with overhead added to it, basically $50 an hour at machine time. So if we remember, our filling time for the first study was 0.73 seconds. We cut that down to 0.49. Our cooling time, we basically knocked almost 6 seconds off of that. So our overall cycle time went from 15.97 seconds to 9.97 seconds. And then our part mass dropped from 7.97 to 6.7. So based on if this was just a single cavity mold, we're saving like almost 9 cents a piece for these parts. So add that up, 100,000 parts over a year, that's over $8,000. That's way more than the cost of the software just for these simple tools. So we're looking at using SOLIDWORKS Plastics as a tool within your design process to optimize your part for the injection molding. So that's all of the presentation I have at this moment. So this has been Jeff Lendermon with GoEngineer. Thank you very much.